Okay, so now we have our second example for designing the controller by the use of an ASM chart. Now the ASM chart is on the left. So when we look at it, we have here there's a state box which is encoded as 00, 0. Now within the ASM block relevant to this state box, so there's a control signal X. And according to the result of this control signal X, we can go to state box encoded as 1, 1. By the way, the first one 0, 0 is called P. The second one that is encoded 1, 1 is called S. I can come here, or there's the second conditional control signal Y, conditional signal Y. And according to the result of this Y, I can go to state R encoded as 1, 0, or I can go to state Q encoded as 0, 1. So the ASM block relevant to P consists of this state box and then the conditional signals X and Y. And these signals determine the exit path. So now when we look at the ASM block corresponding to the state box S, which is encoded 1, 1 as we said. So for S, there are two condition signals, Z and X. So according to the result of Z and X, from state S, we go to state R or we go to state P. When we look at the state Q, the state box Q and the ASM block relevant to this, then there is the input condition W. So within this ASM block, according to the result of W, Q is succeeded by state R or succeeded by state P. So now let's look at this story, how this goes. Now my present, because I have 4 states, I am going to need 2 state variables to encode them, and it's already visible in the name of the state boxes. So I call the state variables G1, G0. So 0, 0 is P, 0, 1 is Q, and 1, 0 is R, and 1, 1 is S. Okay, so now we are constructing our table. Let's look at it. My present state is P. Now we are focusing on the state box. My present state is P. This is shown by the 0, 0 values of the state variables. Now, according to the input conditions, my next states are going to be Q, R, or S. So I write the names of the next states, and I also write their encodings in terms of G1, G0, right? So 0, 1, 1, 0, 1, 1 are possible encodings for my next states. So when do these things happen? I am at present state P. If the input is X prime Y, so X is 0, Y is 1, then I am at state Q. So that is my next state. If X is 0, Y is 0, then I am at state R, and you can see it X prime, Y prime. And if X is 1, without caring about Y, I am at state S. I can decode these input conditions. I can have, so total I have 4 input condition signals. So I can put them as separate columns on the right of the table. And you can see that for state P, we are interested in X and Y. So Z and W are all don't care. And we wrote the required values of X and Y such that the next state is as designated. So I am at state Q here. My present state variables, they have the value 0, 1 because that's the encoding. Now when I am at state Q, if the condition signal W is 0, I'm only controlled by W for state Q. If it is 0, which means that all other signals are don't care and you see W is 0, my next state is P. which is encoded as 0, 0. If W is 1, my next state is R, which is encoded as 1, 0. Now for state R, this is quite nice because we see actually again some state that nothing happens. So I just basically span the clock pulse. We will see why we would have something like this in the next example. So I span the clock pulse only for state R. So for this case, there is no input condition. And all of them are don't care. And unconditionally, basically, my next state is again P, 0, 0. When I am in state S, my present state is 1, 1. If Z is equal to 0, here, if Z is equal to 0, I am going to basically go back to state S, and if Z is equal to 1 and X is equal to 0, if Z is equal to 1 and X is equal to 0, I will go back to state P here. And if Z is equal to 1, X is equal to 1, I will go back to state R as shown here, and they are indicated in the dedicated columns on the right. So now we can apply any of these systematic methods to construct a controller. So we are trying to basically generate the control signals such that the state transitions are happening according to these conditions as designated. That's what the whole idea is about. So what we can do is we can do this D flip-flop idea, right? So I am going to have one dedicated D flip-flop for each state variable, and then I have to provide the correct next state as the D flip-flop input such that when the clock hits, the D flip-flop output creates the correct value for the next state encoding. Okay, now for this example, we are going to extend again this D flip-flop method to the multiplexer method. Okay, so we are going to simply write the inputs of the multiplexer as a function, and then we will generate the output as a function of the selects and the inputs. So for that purpose, what we do is, for the next state variable G1, we look here on the next state column where G1 is 1. So on the next state column, G1 is 1 here. Let's look at it. G1 is 1 here. G1 is 1 here, here, and here. Okay. Now, let's look at it. For the first parts here, G1 is 1 when, now this is the input of the D flip-flop. It is produced in clock pulse T such that in clock pulse T plus 1, we go to the correct next state. Okay, so this is going to be a function of already the outputs of the D flip-flop, which are this G1, G0, the present state, right? And the input conditions. So here, now, G1 is 1 for these two rows. What are these two rows? G1, G0, 0, 0. Okay, it is here. G1, G0, 0, 0. And the input conditions are as follows. So X prime, Y prime, or X. Okay. Now, here, G1 is 1 when G1 prime G0, we are here, 0, 1, W. Okay. Now, here, for the third minterm, for the third basically select combination, there is no case that G1 is 1. So for G1, G0 prime, G1 is 0. And then for the last part, where present state values are 1, 1, G1, the next state, which will be the input of the D1 flip-flop, DG1 flip-flop, is 1 when present state is 1, 1, and the input conditions are XZ and Z prime, right? XZ or Z prime. Let's see it correct. So then this is the expression. Now you can play a little bit to simplify it. So it becomes like this. This is basically simple logic manipulation, algebraic manipulation. Now I do the same thing for G0. I search in the next state where G0 is 1. So G0 is 1 here. I'm searching, G0 is 1 here and here. So G0 is 1 in 3 places. Then you basically write again the expression. So it is for G0, G1 prime, G0 prime, these two rows, this and this. So I write x prime y or x. And then for the next combination, there is no case that G0 is 1. For the next combination, there is no case that G0 is 1. And for the last combination of selects, G1, G0, which is state S, present state, G0 is 1 for Z prime. So, again with algebraic manipulation, this is the input of the D flip-flop who is producing the state variable G0. Then we can build our controller who is going to produce these 4 state signals, right? The idea is that at any given clock pulse, only one of these state signals are active. So either P, Q, or S, one of them will be active. So we prepared the selects of our multiplexers. So the first multiplex here, this is the bottom multiplexer. This is DG0, right? That is what we basically constructed. And the top multiplexer is going to be DG1, the output. So they are preparing the next state ready at the inputs of the flip-flops. These are the present states of the flip-flops. And according to the value of G1 and G0, 2 to 4 decoder makes one of the outputs 1 and the other outputs are all 0. So this output of the decoder is going to be the state signal. So one thing I would like to emphasize is that this procedure that we went through, it's very systematic. You don't need to think much. You could, in principle, write some C++ code to do this from the table. Constructing the table from the ASM chart is something else. But once you have the table, you have the controller in a very systematic, well-defined sequence of steps. Now here we are at the third example. Now we have a circuit, we see the circuit, and there's a verbal description of the circuit. Now there are 2 registers. One of them is in fact a counter, and we have a shift register R1. So the purpose of this circuit is to count the number of ones in the number that is initially loaded in R1. Once the counting is finished, the counter R2 will have the binary representation of the number of ones. So if you think about it, actually, this is if this is a 4-bit register, then you can have 0 ones, 1 ones, or 2 ones, right? If it is a 4-bit register, then you can have 0 ones, 1 ones, 2 ones, 3 ones, and 4 ones, for example. So the counter will count the number of ones in your register, whatever number that you loaded. So the idea works as follows. Every clock pulse after the load happens, we are going to serially shift left the content of the register R1 to a flip-flop E, D flip-flop. Now, when this becomes 1, I mean, when you load an 1 to this flip-flop, which means this is interesting. We should pay attention to this. When we say shift in clock pulse T, so the shift signal is enabled beginning of the clock pulse. So in the transition, when the transition happens to the next clock pulse, that value will be here. And then in the next clock pulse, that value will be here. Okay, so you need one clock to shift the value out of the shift register. So it becomes basically the input of the flip-flop. And one clock pulse, you need to load this number in the flip-flop. Now, when this number is loaded, that is going to be the count for the binary counter. So binary counter will show the result in the next clock pulse. So we are going to go through this with some examples, okay? Example values of this circuit. The operation of the circuit will start with an external input signal S. We designate the state of the E flip-flop with E condition. And then we also have a signal Z. This Z checks whether R1 contains all zeros or not. Because if R1 has all zeros, then you don't need to count anymore. And the counting will stop. So Z is equal to 1 if all the bits in R1 are 0. And Z is equal to 0 if that is not the case. Okay. So now let's think about it. The ASM chart. So we have the initial state, T0. Okay, if start signal is 0, I'm back at T0. I encode it at 0, 0. If start signal is 1, conditionally in this state, so I don't do anything unconditional in state T0 in terms of data path. Okay, so we don't do any register operation, we don't do any flip-flop operation unconditionally. If start is 1, now conditionally, we are loading R1 with the numbers that we count the ones. So R1 is loaded. And then R2 is loaded with all ones. So I don't initiate it with 0. Let's see. Then, clock pulse. I come to the next state, T1. In this T1, we increment unconditionally R2. So this means that when I'm exiting T1, R2 has, right after the initial state, because there is some loop going in, okay? So I will come back to T1 from time to time according to the conditions. But the important thing is that after the start signal, when T1 is happening for the first time, unconditionally, the counter is reset. So the counter will have all these 0 values at the end of T1. When T1 is transitioning to the next state, whatever that next state is. We will see with examples. Okay, so within T1, I have the Z signal which checks if all bits in R1 are 0. If that's the case, now you see that if everything is 0, then I will go back to initial state. How do I go back to initial state? After the clock transition, and everything will be 0 in R2 because there are no basically ones. If Z signal is 0, so which means there is at least one 1 loaded in shift register R1, then I am transitioning to the next state. In the next state T2, I will do the shift of R1 to E. So I will basically apply shift left. Then in T3, I am going to spend one clock pulse such that the thing that I shifted, the bit that I shifted from R1 is loaded in E. So that is the time I spent to load E. Within the same clock pulse now, and when I'm transitioning from T3 to the next state, that's a conditional transition, E is checked. If E is equal to 1, then it means that I shifted a 1, then there is some 1 in R1. So I have to count it. I go back to the counting state. So that will be recorded. If E is equal to 0, then I go back to the shifting state. I simply skip that bit because it had a 0. So I'm not counting it. So that is the main operation for the ASM chart. So as you can see, we need to think which operations can happen in the same clock pulse, and for which operations you have to spend some clock pulse such that it happens. So now we are going to look at an example. Let's look. Here, we will look at a 3-cycle operation. Initially, I'm in the initial state, T0 is equal to 1. What happens in T0? Let's look at this. The start signal is checked. So, of course, to make the example more interesting, S is equal to 1 for some reason. The start signal is checked. So, because S is equal to 1, now conditionally, I will be doing these register operations when the clock transition is happening to the next state. And because of S now, the next state is T1. So the next state of T0 is determined by S, and S is checked because of that the next state is T1. When the clock pulse is happening, so when there is the transition, the positive, these are all positive edge triggered. So when there is the transition, now we will load R1 and R2. Let's say that parallel input of R1 had 4 zeros. Okay, these are, the example is a 4-bit example. So the parallel input of R1 has 4 zeros, 0, 0, 0, 0. And R2 by definition will be loaded with all ones. This is happening in this transition of the clock pulse. So now, according to the ASM chart, I am at T1. At the beginning of the clock pulse, where the controller sets the signal T1 active here, okay? So now T1 is 1. I am in state T1. At the beginning of this clock pulse, already because of the things that happen in the transition, R1 now has 0, 0. R2 has all ones. Okay, now I am here. Unconditionally, I am going to increment R2. Okay, so I am going to here, when I am in this state, I am going to increment R2. So R2 will be incremented to 0 when transition to the next state. Whatever the next state is now. At this point, I don't know. This is an unconditional data register operation. Okay. Now, to determine the next state, possible next states are T0 and T2 at this point. I am checking the Z signal. What is the Z signal? Z signal is a combinational circuit here that checks if all zeros in R1 are 0. Okay. I am checking the Z signal. Everybody is 0. So Z is 1. So this tells me that because of this condition, I will transition to the initial state T0 in the next clock pulse. So whatever is going to be written here is now determined by checking the Z. Transition from T1 to T0 in the rising edge, this register operation will take effect. R2 is going to be incremented. Now R2 becomes 0 because at the beginning it was all ones, right? R2 becomes 0. And I am in the initial state. operation is stopped. R2 has the number of ones in R1, which are 0. Okay, so there are no ones. So this is one case. So we will look at a little bit more complicated case in the next slide. Now assume that, let's think. Assume that now we have the same ASM chart, same circuit, we just have a different scenario. T0, S is checked, S is equal to 1, so the next state is T1. During the transition, these laws are happening. So now it turns out that parallel input of register R1 has this number. Okay, it's 8, 1, 0, 0, 0. R2 is loaded with all ones as before, no problem. And we transitioned to state T1. In the beginning of state T1, the system sees an R1, 1, 0, 0, 0, and the system has an R2 loaded with all ones. Now, unconditionally, I will increment R2. So, increment signal, the count signal is enabled in state T1. And then we will check Z in state T1. When we look at the content of R1, Z is going to be 0. So the next state is going to be T2, according to this. Now clock pulse is sitting. What will happen is that this increment will take effect. So beginning of the clock pulse where T2 is equal to 1, we will see 0, 0, 0, all zeros in R2. And I start executing, now I am in T2. Okay, now in T2 here, unconditionally, we shift R1 into E. And there is nothing else. So what will happen? When we are, and unconditionally, we will go to state T3. Fine, so this is determined. When we are transitioning from state 2, T2 to T3, what will happen? This R1, the content here, it was this 1, 0, 0, 0. It will be shifted. So here we have the 1. And then we have these zeros. The shift is happening in the transition. So as you can see that now the 1 is at the input of flip-flop E. But E still, we don't know what it has, okay? Because we started running the system from the beginning, you could have cleared E in the beginning or it could have any value. We don't know. So here, actually it should be cleared because we don't want this to count randomly. But we will look at the control signals and the data path. So here, 1 is ready. Okay. And then the next operation, we finished T2, E is at the input of 1 and we are at this state. So the shift operation happens in this transition. So R1 becomes 0 at this edge. Now we are in the beginning of T3 where we are not doing anything with the register, but one thing will happen. Now T3, clock is hitting. So at the end of T3, actually unconditionally, this whatever value we have, and it's not whatever, it is 1 because shift happens only then, this will be loaded here. And then, not then, in the same clock pulse, we are going to check this E, and according to the value of E, we will know what we are doing. So here, the value of E is going to be 1. So this determines that our next state is T1. At the beginning of clock pulse T1, E is loaded with 1, R1 is all zeros. Now what happens in T1? T1 says that unconditionally increment R2. So in the transition here, this R2, the counter, will be incremented. And within T1 ASM block, in that clock pulse, we will check this 0 signal. And indeed, the 0 signal is 1 because 1 is shifted out. So R1 only has zeros. So this determines our next state. Our next state is going to be T0, which is here. So state transition, R2 is incremented. So we conclude the operation by returning to T0 with R2 equal to 1. So initially R1 only had 1, 1. And the system will stop. Now let's think about the data path for this example. So how will we basically control all this load, count, all these operations? Now, actually, when we look at the ASM chart, let's start from the easiest ones. ASM chart, here, R2 is incremented when we are in T1, no matter what. So I simply connect the T1 output of the controller logic to the count input of R2, done. What else happens? Here, T2, unconditionally, when I am in T2, we apply a shift left operation on R1. So the shift input of R1 is connected to T2. Okay, now let's think. When do we load to R2? And what do we load? All ones, parallel input. When does this happen? When I am in state T0 and conditional signal S is equal to 1. So S is equal to 1 and this is T0 and this is the load. And it's also the load for R1. There's a zero check circuit, fine. So when do we get something on here? When we are in state T2, and if there is a 1 here, then you have a 1 here. Otherwise, if I am not in state T2, then this D will be 0. Or if this is a 0, the most significant bit, then this is a 0. So in the next clock pulse, whatever happens is loaded. So next clock pulse, you would load a 0. So you only load a 1 when we are in state T2. And the most significant, the most left bit of shift register R1 is a 1. So this is the data path. For the data path, we see the register operations, we see the signals that trigger the register operations, and these signals are produced by the controller logic. These are the state signals, and also sometimes we use these external input signals, okay? The zero check circuit is simply some NOR of all the bits. Now we will do the control circuit. So we will create again this T0, T1, T2, T3. We have our table. The table is generated from the ASM chart. So we can look at it. We name, again we need two state variables. G1, G0. T0 is 0, 0, T1, 0, 1, T2, 1, 0, T3, 1, 1. So here we write the next states. These are conditions. So next state is T0 if the start signal is not activated. T1 if start is 1. For T1, it goes back to next state if everything is 0. It goes on if that's not the case. For T2, I transit from T2 to T3 without any condition, input condition, just with the clock pulse. And my next state is T3. And for state T3, I have two possible next states according to the value of E. Okay, so if E is equal to 1, I am going to count. So I go to T1. If E is equal to 0, then I am going to skip that bit and check the next one if it is 1 because I want to count. So I go basically skipping it is T2, which is this shifting. Okay, so again in the table regarding G1, I find the rows that G1 is 1. I have 3 terms. And then I write these terms here for the max implementation. And regarding G0, again, I find the rows that it is 1. So it's here and here and here. And then I write it. And this will be the selects for the multiplexer. So again, we have the multiplexer and the decoder implementation. So we give the correct inputs, and these inputs appear at the outputs of the multiplexer with the correct select, and they will drive the flip-flops D1 and D0 to the next state, such that in the next clock cycle the decoder activates the correct outgoing signal, the state signal. Next example. Now, in this example, again we have here the initial state T0. The ASM block with the state box T0 contains this conditional signal and the conditional data path register operations. We have the next state box T1. And then from T1, here there is a comparator. So the comparator has 3 possible outputs. According to the value of the output, from T1, you can go to T2 or T3. And from both T2 and T3, unconditionally, the system goes back to T0. So we are going to design this system. Now, what are the data path signals? Now let's think. We will have the controller logic. We will design. The controller logic is going to produce, please do not forget, the controller logic is always a sequential circuit. It's with the clock pulse. The controller logic is going to produce the state signals T0, T1, T2, T3. The inputs for the controller logic are this conditional signal S, output of the comparator X, Y, Z. Now, according to the state signal, things will happen to the registers. So we have a register A, register A, register C, and register B. Now, one thing is that if the start signal is 1, conditionally A and B will be loaded, parallel input, right? So if S is equal to 1 and we are in state T0 here, A is loaded. Same for B. If S is equal to 1, we are in state T0, B is loaded. So this is the data path. Register control signals. We are producing the register control signals. The register control signals depend on the state signals and the conditional signals. Okay, so we will produce the state signals in the next step. Now we are looking at, so we saw that conditional we load A and B. Okay, and then in T1 there is no unconditional operation. However, I am in state T1 and X is true. So for the comparator output the way that we defined. If x is true, then conditionally with this T1x, we are going to shift left A. Here you see T1x is the shift left control. We are in state T1. T1y, I will shift right B. So now look at my register B, T1y is the shift right. Okay. Now, what happens to the register C? Now, register C has two unconditional loads. When we are in state T2, register C is loaded with A. When we are state T3, register is loaded with B. So now C, parallel load. So let's say this register has, you can do it with a multiplexer, but assume that we have separate inputs. So here I have parallel input A, parallel input B. From A, from B. So if I am in state T2, then if I am in state T2, then I am going to, but there is one more thing here, sorry. Now, how do I come to state T2? So there is this condition basically. So now this state T2, arriving at this state, it happens, or I load this, I arrive this state and I load it if I am in state T1 and then Z happens. So I arrive at state T2. So that is load A. Or I am at state T2 and I load it. Okay, now we are doing the data path design for this example. So we are going to define the control signals for the registers. Okay, now when do we load register A and B? Let's think. We load register A and B with parallel input when we are in state T0 and the conditional signal S is equal to 1. So for register A and for register B, the parallel load is ST0. Now what else happens to these registers? When I am in state T1 and the conditional signal X is 1, then register A is shift left. When I am in state T1 and the condition Y is equal to 1, then register B is shift right. When I am at state T2, the register C is unconditionally loaded with A. So load A is T2 for register C. And when I'm at state T3, C is unconditionally loaded with B. Load B is T3. Okay, so the controller logic. So the registers are all, of course, with clock pulse. Controller logic is with the same clock pulse. And now we are going to define also the controller logic. So it is going to produce T0, T1, T2, T3, the state signals is a function of the input signals S and the result of the comparator. So from this we are writing the controller. When we are in state T0, again we have variables G1, G0 for the states. So when I'm in state T0, the next state is T0 or T1 based on the value of S. When I'm at state T1, the next state is T2 or T3 based on the value of X, Y, Z. And when I am at state T2 and T3 here, the next state is unconditionally T0 without any extra check. So with the clock pulse, you go to state T0. So we apply the multiplexer method. We check for G1 where G1 is 1. So G1 is 1 here and here and here. So G1 is 1 when you are in G1 prime G1 prime G0 without any condition, and the remaining parts are all 0. So for if you look at the multiplexer inputs, this will be 1, the multiplexer that is producing DG1. This input 1 will be 1 and the rest inputs will be 0. Now regarding G0, when it becomes 1, here and here. And when does this happen? Input condition S and Y. So you find that for G1 prime, G0 prime, when S is equal to 1, this is going to be 1, so it depends on S. G1 prime, G0, here it's Y, that defines DG0. So I connect these to the multiplexer inputs. The remaining inputs of the multiplexer are all 0. So based on the selects, which are going to be the present state variables, the next state will be arranged by the multiplexer output. Okay, next example. So we learned combinational multiplier at 348. We did the circuit, so it was basically all these adders and so on. So now we are going to do a sequential binary multiplier. So we will do it with two algorithms. We will first look at the first algorithm, but we won't implement it. The second one is more interesting and it is more efficient, so we will implement it with an ASM chart. Now here we have two numbers. So this is, we are multiplying B with Q. We are multiplying B with Q, and the result is going to appear in A. So in this setup with this algorithm, we are going to need two n-bit register B. We are multiplying B and Q, which are both n-bit numbers. So we will need a register B. We will see how it will work. We will have a register B with 2 n bits. We will have a register A with 2 n bits. And we will have the register Q, which will initially also hold the multiplier with n bits. So the algorithm is as follows. So we are going to initialize this register with 0. And we will keep some counter I, such that we know that we multiplied all the bits of Q. So we initialize I with the number of bits, which is 4 for this example. And then in a loop, we will check if the current bit that we are multiplying, which is always going to be Q0. If Q0 is 1, we are talking about now the register, okay? This point, this bit stored in this location. If Q of 0 is 1, then we are going to add the multiplicand to the current result. So A is going to be loaded with A plus B. Then we will shift right Q. We will shift right Q. So we will start with the least significant bit of the multiplier, and then every time we will shift right to go to the higher significance. So Q will be shifted right. And then this B, we will be shift left. And then we are going to decrement I until I is equal to 0. So you can see that for this algorithm, we are going to need all the registers to have shift capability. Now we are going to do a more interesting version. So we will do it with a smaller b. So we will only have n bit register for the multiplicand. We will have q, m bits, and we will have a, n bits, we will have a 1 bit carry. And the algorithm is as follows. So the idea is that we will keep adding when the least significant bit of q is 0, which means we always process the least significant bit of q because we are shifting. And if it is 0, then we are not going to add. So this is the algorithm. Now what I want to do is we are going to go through this in steps with this number just by hand multiplication, just to have the feeling of it. Then we are going to construct the ASM chart. Okay, so we are going to look at, for this second algorithm, we are going to look at a register 2n plus 1 bits. Actually, the last is the carry, and then 2n is basically, this is A and Q. Okay, so now let's look how this is going to work. Here is our example. Our multiplier is Q1101. I always keep the algorithm here such that we know what we are doing. Remember, we have the CAQ, 2n plus 1 bit here, set up. Initially, we reset C, A is reset, and then we set I is equal to 4 because we are going to do a 4-bit multiplication. Then in the first iteration, we decrement I. So this is iteration 1. We will do 0 and then we will finish. We will decrement I. And then now we are looking here. Q is, by the way, of course, this is already there. Our multiplier. Okay, Q was already loaded. So initially we are at this stage. If Q0 is equal to 1, now here, okay, then CA, these two parts, is A plus B. B is fixed. It will be in some register. Now we are looking at CA. A is 0. A plus B is this. Q is still sitting here as it is. Now we have done that. Now we will do a shift right by inserting 0 from the left to C, A, Q. So we will shift right this thing. So now we inserted the 0 from here. And now that 0 is here. This 0 is here. Everything is shifted right. This fell off. So that is the state of CAQ. We go on. That is where we were from the previous run. We were here. Now the algorithm says first decrement. Okay, we decremented. Now if Q0 is 1, do something. The add. If not, just skip this step by shifting right CAQ. So we are looking at here. Q of 0 is 0. Which means we don't do add, we just shift, inserting a 0. So here you see that 0 is inserted, these are shifted, and then this fell off. Now we are like this. Check, this is 1. And then we are going to add, because it means that now we have to add the B, right? So we are going to add B to CA. So here, this is the state of CAQ before the addition. If you add this number, then you will get this. Okay? And then we are going to do the shift right. So we end up like this. we go on here again. We check the least significant bit. Okay, so which means I'm adding again. So CA is A plus B. So we have this, and this is the last shift. We insert 0 from the right. Everything is shifted. Now we were decrementing this I every time we were going through this loop. So now I became 0. The last execution happened when I is 0 until I is equal to 0, finished. Okay. So that's the ASM chart for it. If we look quickly for this ASM chart, one thing is that there is the control signal, that is we are checking here P0, and it is basically obtained by decrementing the counter, the number of bits here unconditionally. So after, when we are preparing for the run, in the initial state, if start signal is 1, then we will load A is 0, just we said, C is 0, counter is loaded, B is loaded with multiplicand, Q is loaded with multiplier. And then we start running it by decrementing, checking. If it is 1, add. If it is 0, do nothing. For both of the cases, shift right by inserting a 0 from the leftmost position. And then check if the counter is finished. If the counter is finished, then I go to the initial state. If not, I do the whole thing again. Okay, so now we are designing the data path for this circuit that we talked about. So we can look at the basic operations. Now, when we are exiting the initial state, we are going to do this conditional loads, right? So when we are doing the initialization, we call, to make it simple, the initialization signal as load init. This is ST0, S is equal to 1. I'm at state T0. So when this ST0 happens, what are the things that happen? Counter P will be parallel loaded, okay, with N here. Next, B and Q will be parallel loaded with multiplicand and multiplier. So load init is connected to their parallel load. It has to, register A should be cleared. So A has a clear input. Load init is clearing register A. Now for this C has to be also cleared. So we are basically providing an input for C flip-flop with a multiplexer. So if the multiplexer select is 0, then C is going to be loaded with 0. And if the select is 1, then C is going to be loaded with the most significant bit of the sum, A plus B. Okay, so now if you think about this, initially, so the select is controlled by the add signal, and add is for this, right? So add is happening when we are in state T1 and Q of 0 is 1. Okay, that's add. T1, Q of 0. Now, if in the initial state, add signal is 0 because T1 is 0. So C will be loaded by 0. Whenever we are doing this addition, C will be loaded, add signal will be 1. C will be loaded with the most significant bit of the sum. Here that is the parallel adder here. That is adding B and A. Okay. So here B and A, they are added together and it's loaded to C basically. The most significant bit is loaded to C, remaining is loaded to register A. Here P0 signal is created with the combinational NOR to check the counter. So now we need to define shift right, unconditionally. When we are in state T2, we are shifting right CAQ. So the shift right signal of A is counted, is connected to T2, unconditional shift right. And when I am at T2, yes, I am doing this unconditional shift right by entering 0 from C, which means I am not doing the add operation. So here there is a 0 ready. It is going to go in and insert it from the leftmost position for the shift right. Okay. So we can do the controller logic as before using the multiplexer method. So we simply translate this ASM chart to this table. So now our states are T0, T1, T2. These are the state variables. Next state variables. The input condition, the conditional is happening is by the state transition is the start signal and the P0. So you can write the multiplexer inputs. Basically the multiplexer inputs are 0, 1, 0 for the G1 and S0, P0 prime for G0. Now we can implement this with a different method as well, with one flip-flop per state. So now we are going to have, we won't have this decoder, but we will have D0, D1, D2. And one of these flip-flops will be active at a time. So how do we go to the next state of D0, right? This is going to be the input of the D0 flip-flop. Let's think about it. How do we go to the next state? So here I return T0 if S is equal to 0 and I'm already at T0, S prime T0. Or I arrive T0 from T2 when P0 is 1. So that is this. For D1 input, for T1, you arrive T1 either you are at state T0 and S is equal to 1, or you are at state T2 and P0 is 0. You arrive T2 unconditionally from T1. So that is basically the input equations. When you follow the execution, this is basically what I did, but we did it logically. This is basically as follow of the operation together with the status signals and the next state and the output signals, okay? So it's always the same number. Multiplicand is this, multiplier is this, n is equal to 4, s is equal to 1, so we already started the operation. So we are at T0, we are now looking at the ASM chart as well. When I am at state T0 and s is equal to 1, then the next state is T1. What is the signal that is active? It is this load init signal. Okay, s is equal to 1. I am in state T0, so load init is 1. And this is going to basically do all these conditional loads at the end of the clock pulse. So now in the next clock pulse, we are in T1. We are in state T1. So unconditionally, first of all, I decrement. So when I am in state T1, you can see that this decrement is 1. Okay, unconditionally. So I'm stating T1, 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 and T1. Okay, I do this. Then in this state, I check Q of 0. If Q of 0 is 1, then I am going to add. If Q of 0 is 1, the add signal is activated. If Q of if I am add signal is activated and I come to state 2. If Q of 0, I am in state T1. If Q of 0 is 0, then add signal will not be activated, but I will still go to state T2. Okay, so here I do this. And then in the beginning of next clock pulse, for T2, now I'm here. I do unconditional shift right of CAQ. So T2 raises unconditionally the shift right signal. You can see it every time. And then from T2, I have two possible next states. So the shift right is executed and we check P0. If P0 is 0, next state is T1. If P0 is 1, next state is 0. So when I'm at T2, two possible cases. For this case, P0 is 0 here. So the next state will be from here. The next state, wait, this was T1, sorry. I am at T2. I'm doing this, okay. The shift right signal was activated. That's okay. And then we will check P0. P0 is 0 for this one. So this is going to imply that the next state is T1. There will be only one case as we go through the operations where P0 becomes 1, and that will imply next state is T0. So until the multiplication result appears in the register, and we understand that the multiplication is finished by P0, we keep doing this. We basically go between T1 and 2, T1 and T2. So we are looping here. And then this last condition will take it back to T0 with the correct result. So this concludes the lecture for algorithmic state machine.